Okay, so here are Brenda and Layla, and they are demonstrating Brenda's technique of fog reduction for your goggles. So if you put a paper towel under your goggles a little bit, it tends not to fog up as much. And they just had them draw some mustaches on there for fun. So today we finished chapter 5. I'm just going to do one other thing. I guess I didn't technically totally finish it, but I'm just going to add on the StereoChem component in nomenclature, which I haven't really talked about. And I made the organic chemistry step-by-step file easier to navigate. I took the first 8 weeks and I added them to a second sheet. So if you look down on the bottom of that file, that sheet, you'll see sheet 1, sheet 2. If you go to sheet 2, you can look at the week 1 through 8 links. And then the first sheet you come to is 9 through 10, 11, 12. It makes it a little easier to navigate. You have to scroll down this far. And it's best to watch these lectures live, like those of you who are here. Thank you for coming. I'm glad you can. But if you can't come to a live lectures because you have another class or something, then at least read through the lecture outlines. These outlines I'm going through now, because it'll keep you on top of what's due, what's coming up, changes, things like that. So try to at least click through those because that should only take a few minutes. And then StereoChem quiz. We have a quiz I made a mistake earlier this morning. I said it was Monday, Tuesday, but it's Tuesday, Wednesday. I wanted to give the Monday, Wednesday lab people a little more time to study for it since I didn't announce it till the end of last week. But then my plan was, when I thought of it, I was like, oh, I'll make it in Wednesday, Thursday lab. But then Thursday, we don't have a lab for Veterans Day. So I was like, oh, okay, let's do it Tuesday, Wednesday. And then I got it mixed up. Homework E, chapter 6. I finished that one and it's posted now. We're going to start chapter 6 this lecture today. Chapter 6 is kind of a little bit shorter chapter. It's just one reaction, but it's setting us up for chapter 7 when we add on 3 more to that first reaction in chapter 6, the SN2 reaction. So start that homework early. And I updated that homework this morning. I added a lot of good stuff to it. I added a couple at least problems from last year's exam. So you get like exam-like problems and problems the way I've been thinking lately. And then homework 5, that's due this week, Wednesday, Thursday. I know Thursday's Veterans Day, but you could turn it in late or early. And we don't have lab Thursday, so you could try to turn in Tuesday if you can. And I should have made that due date earlier, but that's okay. Some of you, when you're turning in your homeworks, or homeworks aren't as big a deal, but like some of the assignments, you're having trouble with uploading them. And when you upload them, there'll be just photos of your handwritten work. But if you have handwritten work, go ahead and turn that in person. Just hand that to me. It's easier for you and easier for me to grade. Let me check the chat here. Do I have a question? I don't know if there's a key for homework 5. I'll look, I'll see. And prepare for lab this week. Try to finish extractions on Monday, Tuesday, and then so you can start the chromatography this week. I know Monday, Wednesday lab students have 2 lab periods this week. Tuesday, Thursdays don't have Thursday, but if you can, try to get as much, let's get going on that. And read ahead, like so if you read through to a point where you have to start wet chem, you can skip ahead to the next intro so that when you come into lab, you can get the data quickly. And then tutors are needed for the spring. Ask me for recommendations. So I haven't heard from anybody yet. So are any of you who are live interested? And Carson was asking about a Zoom meeting for Thursday's lab. No, since it's a holiday, we'll just have the holiday. But if you have questions, if you're studying or whatever, email me. So I give tutors a +1 point extra credit. So if you are a tutor, let me know and I'll give you an extra credit point. And if you have never been a tutor, you should consider it. It's really helpful. It helps you with your studies. Okay. Oh, that's what before the tutors things. I entered zeros for some crystallization labs that weren't turned in, and this might mean that you tried uploading and it failed or something. But when I enter a 0, that seems to alert students to, oh, wait, what's going on? So that's why I did it. So let me know if there was an error so that we can get you, get your work graded. And I entered zeros and some other things too. So if you're feeling like, oh, that wasn't fair, let's just talk to me. We'll figure it out. Okay, that's what it is. I'm going to stop filling in the due dates. I mentioned this before in the Google Sheets. It's just kind of a lot because I was putting in the due dates in the Canvas assignment, in the step-by-step, and then that due date sheet is just like, and then I forget one or one would be different. It was just, I'm making too much work for myself, but you know the deal. And a lot of you are turning things in like 4 days late is like just your norm. Try not to be like that. Try to turn it in on the due date. And this could be your saving grace. This shouldn't be your go-to. All right, and then you can come to lab and work early if you like, as always, today 1 to 1:50 if you want. And let me know about your progress on the new GSAs today and tomorrow in lab. Let me know, I should say honor students. That's what I want. And then if you're not doing well, like I said before, come to office hour, make it your new class. Come with questions or not. Most people come without questions. And then, oh, and then also besides coming to my office hour, go to Morgan's past peer session, because you can go without questions too. You say, hey, Morgan, can you write me up some questions? And he's great. He can do that. And adding StereoChem to nomenclature. So this is a question from homework 6. Homework for chapter 6. I realized I didn't really do this in lecture, and I kind of wanted one of these on the homework. So I added it to homework 6 and 5. For those of you who've already started 5, you don't have to do it. It's going to be in homework 6. But so what it is, it's just showing you how it's easy to add nomenclature, the opposite StereoChem, to your nomenclature. So this one on the left, it's got the R stereocenter for the bromide because it's A, B, C. Yeah, that's R. And then this second carbon here, the one with the iodide here, our third carbon from the left, it is A, B, C, it's S. Yep. So what do? We mumble over our words. We name it like we normally do. So this would be 2-bromo 3-iodo 4-methylpentane. Why did I number from the left? Can anybody tell me why I put the 1 here to make a 2-bromo versus a 1 here and a 2-methyl?
Is it alphabetical between bromine and iodine?
It's not really bromine and iodine. So before we go alphabetical though, what do we want to have?
The lowest numbers on the chain.
Yes, and if I number from left to right, I'll have a 2, 3, 4. And if I number from right to left, I have a 2, 3, 4. So either way, I got 2, 3, 4. So then the tiebreaker becomes between the bromine and the methyl, not the iodine. It's whatever's first in that chain. So you were almost there, Ryan. So bromine is B before M for methyl. So that's why I was numbered that way. So once you have that part of the name, then you just put out front in parentheses the carbon numbers in their stereocenter. So it's 2R3S, 2-bromo 3-iodo 4-methylpentane. So you see it's kind of repetitive, the 2s and 3s, but that's just that's the format that the Colin Ingle-Prelog and the old chemists at IUPAC came up with. And then if you look over here, the enantiomers, where I switched, the R to the S on the bromide and then the S to the R on the iodide. So those are going to just be 2S3R instead of 2R3S. And then everything else is the same. Yep. There we go. And then, oh, and then this kind of nomenclature, R and S part of the nomenclature, that'll be on pretty much every exam. I've come up with the idea, and it seems to be true, that if I just always ask you to calculate R and S for molecules on nomenclature questions that I put on every exam, you don't lose that skill, but we'll be using the R and S constantly too for other things as well. Okay, so just about everyone who's turned in the Stereochem workshop missed question 9. This one. It's a tricky one. It's got all my best tricks in it, but it's good because I want you to be tricked by it so you learn from it. But I want you to be tricked by it on this Stereochem workshop and maybe on the homework, but I don't want you to be tricked for it on the exam because that's where you lose a lot of points. So don't get tricked on the exam on this one. So let me help you with this one. I'll start the lecture off with that. Go over to my Jamboard here. So here's a partial Stereochem workshop key. Stereochemistry workshop from all right, here we go. So are these same, different? How are they related if they're not, if they are different? So if two molecules are superimposable on each other, then they're just the exact same thing. So let's check for that. Get my Jamboard opened here on my iPad. So let's look at molecular formulas first. This first one is C1, 2, 3, 4, 5, 6, 7, 8, C8H, 0 degrees of unsaturation. So I just take 8 times 2, 16, 17, 18. So this one's also C8H18. Let me double check that. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 16, 17. So they have the same molecular formula. They could be isomers, or they might be the exact same thing. Let's see. Is this a stereocenter? Is this a stereocenter? Does that have, is it tetrahedral? Yes. Does it have 4 different things attached to it? No. It's got 2 ethyls. It's got an ethyl here and an ethyl here. If I was thinking it were a stereocenter and trying to assign priorities to it, then I would say, oh, this has got a hydrogen lowest priority. I got a CH2, CH2, CH2. Oh, wait, they're exactly the same. I can't decide which one's A or B priority because they're exactly the same. So these are not stereocenters. That's a big key to this one. So don't get confused just because it I wedged and dashed those. It doesn't mean they're stereocenters. So these are not stereocenters here and not there. Okay. Now what I'll do is I'm going to rotate this one. I'm going to take it, I'm going to rotate it around this bond. I didn't give myself enough room. I'll make it blue. I'm going to rotate around this blue bond in such a way where I make the carbon that's the ethyl that's dashed back. I'll call this like A and B. I'm going to make A and B rotate around to be in the plane of the page. And that means that then the hydrogen that's on here that hydrogen right there, where will it go? If I take A and B, I rotate it down to the plane of the page, where will this hydrogen be? Will it be dashed back, in the plane up, or where will it go? If I do that rotation, the hydrogen will dash back. It's just basically the H is going where the A is and A is going here. So then this chain right here is going to be where? It's going to be wedged. So here, I'll number that too, so make sure it makes sense. Let's go 1, 2, 3, 4, 5. I'm not numbering this like nomenclature rules, but just numbering it to help me see it. So it rotated up that way. And now the reason why I did all this is to show you that, oh, wait, this is exactly the same. Same molecule. Almost everybody said they were enantiomers. They're not enantiomers. They're superimposable, same molecule. So if they're the same molecule, then are they meso? That was the other thing I said. Are they, if they're the same molecule, are they meso? Same meso molecule, or but not meso? You know. So meso, are they meso? Let's see. Are they? Is it meso? I shouldn't say are they, because are they suggests there's more than one like they're different molecules. Is it meso? Because this is just one molecule drawn twice. Is it meso? Well, it needs to be superimposable on its mirror image, which it is, yes. But it also needs a chiral stereoisomer to it. So does this have a chiral stereoisomer to it? Does it have like a stereocenter? Like, well, we have one stereocenter, so we have 2 to the 2 possible stereoisomers, or 2 stereocenters, 2 to the 4. Does it have a? Has none. Does not have it. So it's not meso. So these guys are same, not meso. Okay, done. Now this next one, are we going to be fooled again? How many stereocenters did this have? Well, this first one is a stereocenter for sure. Boop, boop, boop. That's a stereocenter. This is a stereocenter. But this other one, is that a stereocenter? Tetrahedral. Does it have 4 different things attached to it? Not a stereocenter. Doesn't have 4 different things. It has a methyl here and a methyl there. They're exactly the same. Not a stereocenter. So actually, I can actually draw them up differently since they're not even stereocenters. I can draw them up like this, just not show the wedge or dash on that. That's fine. And then this one could be drawn up as. So if that's the case, they're not a stereocenter. I just have one stereocenter, and those stereocenters are opposite configuration, like this one over here. Let's see what it is. We got A, B, C. This one's S. And then we got A, B, C, yeah, R. So what are these two? Are they mirror images? These ones are enantiomers. Enantiomers. Not diastereomers. Most everybody I graded the workshop put diastereomers for these because they thought this was a stereocenter, but it's not. Okay, now this next one, these alkenes, there's no rotation about the double bond because it's a double bond. It has pi bonding, and the pi bonding is overlap of p orbitals above and below the internuclear axis. And then if it rotates, it would have to break the pi bond. So if we're having to break the bond, we're doing a reaction, and then you're making a different molecule of products, you know, a different thing. So this is no rotation here. So this one we call this the trans, and this one's the cis. So they are definitely different molecules because they can't superimpose on each other. They're different. Same molecular formula. same connectivity, different three-dimensional arrangement in space, right? So they're stereoisomers. Are they mirror images? Are they mirror images? No. So if they're not mirror images, they are diastereomers. We do a lot of examples in which the molecules have the absolute configuration stereocenters with like RNS, but that's not the definition of a diastereomer. Definition of diastereomer is, are you stereoisomers that are not mirror images? Doesn't say anything like you have to have stereocenters. So they're diastereomers. Okay, next one is the same sort of thing. If I were to rotate this one, let's say I take this guy and I rotate it this way in the plane of the page, it would look like this. And then I'll go H. If I do that, just do a quick little easy rotation like that in the plane. What is that? 90 degrees. Then hopefully you see these are definitely mirror images. They have the same molecular formula, same connectivity, and they do differ in 3 dimensions because if I try to superimpose them, they're not superimposable. So these ones are enantiomers. Oh, let me show you something really quick. So am I sharing my screen right now? I am, yeah, good. Doesn't look like it. Oh, did I draw it right? So Santos was asking about how I drew the chlorine, the dashed chlorine on the right versus on the left. It doesn't matter. If I put the wedge on the wedge hydrogen on this side and the chlorine dashed on that side, it's just a matter of viewing it like, oh, I'm viewing it this way or that way. Just the skew of it doesn't make a difference. Same molecule. Okay, and then, oh yeah, let me show you this really quick. So we did this at the very beginning of the stereochem stuff, but it's been a long time since you saw that very beginning. And when I did it in the beginning, I was saying that, oh, this is going to make sense later, all the stereochem and everything about it. So let's just quickly click through this to show you what I mean. I'm letting it load. I think I got it. Yeah. So isomers, different molecules that have the same molecular formula. Constitutional isomers are isomers that have different connectivity. And then stereoisomers are isomers with the same connectivity, but they differ in 3 dimensions and spatial orientations. So we have these two down here. So these two are cis and trans isomers. They are both same molecular formula, same connectivity. Are they mirror images of each other?
I'm gonna go with no.
They're not mirror images. So if they're not mirror images, they are called what? Diastereomers. And these particular diastereomers have stereocenters. So we have like 1R, 2S, 1R, 2R. And diastereomers do follow that pattern where like some of these stereocenters are the same, 1R, 1R, and some are different, 2S, 2R. Okay, so that's that. But then these next pair of molecules down here, one of them cis and one of them's trans. What's this left one here? Trans. This one's trans, and the one on the right, cis. Okay, so they have the same molecular formula, same connectivity, the different 3-dimensional orientations. And are they mirror images of each other? They're not mirror images. So what are they? These two are diastereomers. And there's one more thing we haven't done yet. This is the E diastereomer, and this is the Z. We'll talk about what that means later. I'll just give you a little clue. So the two methyls on this one are on Z same side. Z same side. Let's talk more about that. Okay, and then I went through examples of enantiomers that have a stereocenter. These two are enantiomers, right? They're non-superimposable mirror images, and I showed how if I tried to superimpose them, when I flip things around, the OH and the H don't match up. So these are more common enantiomers, but this here is also enantiomers because they're mirror images and they're non-superimposable. Like if I take the left one, I flip it over, it won't superimpose on its mirror image. This is still enantiomers. So this is enantiomers that contain chiral centers or stereocenters here, enantiomers that have no chiral or stereocenters here. So, and then here's the equivalent diastereomer pairs. So diastereomers are not mirror images. So these, you can see trans and cis, not mirror images. They have no stereocenters, but they're still diastereomers. These ones do have stereocenters and they're diastereomers because they're not mirror images. But the definition of a diastereomer is stereoisomer, not mirror image. The definition isn't stereoisomer with some R's different, some S's different. So just don't mix that up. The RS thing is a great trend to know, but it's not the rule. Okay, we are good to go with that one. Oh, GCMS coming up soon. We are on chapter 6. So chapter 6 is about one reaction, the SN2 reaction. And we'll go into detail about this reaction, and the details we cover about this reaction, that'll lay the groundwork for details we'll look at for other reactions we learn. So we're going to be learning about 4 of the most fundamental organic chem reactions in the next couple chapters, the SN2 reaction in this chapter. And then in chapter 7, we'll add on the SN1, the E1, and the E2. And we have honor students making us up some nice GSAs for these. But first, a lot of these outcomes you can just do on your own, but I'll just briefly talk about them. So a haloalkane is just an alkane that has a halogen on it. Most of our SN2 reactions occur with haloalkanes. So halo like halogen. So fluorine, chlorine, bromine. And in these haloalkanes, it's mostly going to be chlorine, bromine, and iodine, not fluorine so often. All right, and then we remember the size of halogens. Fluorine's smallest, most electronegative, less protons and electrons. Then chlorine's bigger, iodine's bigger, bromine's bigger. And halogens are usually referred to as an X, like we do in our degrees of unsaturation formula. And carbon chains or alkane chains are usually called R's. Not always, but usually you put an R for that. All right, now let's talk about this thing. Well, actually, before I do polarizability, let me just get into the SN2. Let me do it on the Jamboard. Yeah. Well, don't want to do it on the outline. Let me see about the outline real quick. Chapter 6. Yeah, this is pretty good. I'll do this as a start. Ryan, I'm not sure about, I got to think about your question about the RNS. And if they have some R, they have some stereocenters that match and some that don't, I think they definitely will be diastereomers. But if
I may not have asked the question right. That's okay.
That's okay. Ask me again. And then, okay, so SN2 reactions. So when we write out reactions from now on, and we've kind of been doing it already, we'll write out the overall reaction first, where it's like, here's the reactants, reagents, products. And then underneath that, we'll work out the curved arrow mechanism. So for most of our reactions, we will learn the curved arrow mechanism, and that's very helpful because once you have the curved arrow mechanism memorized and down where you can see it in your head, then all the details of the reaction make sense and everything just comes easy. So we're gonna practice a lot of mechanisms, and you'll get better with mechanisms to the point where like you'll see a reaction you've never seen and you'll say, oh wait, yeah, that's definitely going to be deprotonated first, and then oh look, now it's electrophilic there, it attacks there. It makes the subject much easier to understand and enjoy because you're kind of just deriving everything instead of just a straight memorization of reactions, reactant, product, like a computer. We're not going to be like that. We're going to be more like, oh, look at that electrophile. Oh yeah, that nucleophile add there. And so after we've gone over the curved arrow mechanism, which for most reactions we will, then we'll talk about the details of the reaction. Like, oh, this one inverts the stereocenter, or oh, I expect, like we've already done this with halogenations. Oh, with bromine, you expect the more substituted carbon to be the major product. Like, oh, probably get more of that tertiary product over the secondary and primary. And but we won't always go over mechanisms because some mechanisms are just long and they're not as helpful. So we'll just some reactions we'll just learn. Okay, these are the reactants, these are the products. Okay, so an overall general example of an SN2 reaction. You have something called a nucleophile. And nucleophiles are nucleus loving. They love nuclei, like we've said before. And nuclei are protons and neutrons are positive charged. So if you love things that are positive charged, you're negatively charged. That's why this general one I made negative. And then the electrophile, also referred to as the substrate. Substrate is usually used more for biochem, but it's the same kind of thing as a electrophile. So the electrophile is electron loving. They love electrons because they are partially positive charge or full positive charge sometimes. No, usually always partially positive. So they have a positive charge. So they love electrons, which the nucleophiles have extra of, so they react. And then it's a substitution reaction. So there's part of the electrophile that pops off. We call it the leaving group because it left. It's substituted for by the nucleophile. So overall, I'll give you some more overall examples on my Jamboard. It's better than just this generic one. But there's a bunch here on this slide. This would be a good practice when you're going over notes to just draw this overall products and the curved arrow mechanism once I show you it. So before we do that, let's go to the Jamboard and do some of these. That's right. Okay, here we go. So SN2 reaction. So the S stands for substitution. We're substituting a leaving group on the electrophile for a nucleophile. The N is for nucleophilic. Sorry, my Jamboard crashed on the iPad. I don't know what's up with this. Come on. Let's get it back, get it back. Oh my goodness. Can we get to the spring semester and be on a whiteboard again? Can we do it? Can we? What happened? Okay, I had to close out of the Jamboard, back in it. Nucleophilic. So the N is nucleophilic. Those two are kind of easy. You got a nucleophile, say nucleophile in a fancier way, nucleophilic, and then substitution. The 2 is the more tricky one. 2 is just describing the fact that its mechanism has a bimolecular rate determining step. So the mechanism is the rate determining step is bimolecular, and bimolecular means 2 molecules react. So 2 molecules are colliding and reacting in the rate determining step. So that rate determining step is depend on the concentration of 2 things. So for example, well, so the rate law, I'll go ahead and write it up here before I forget. It's some rate constant times the concentration of the nucleophile times the electrophile. And this is determined experimentally. You can tell because if I double the concentration of the nucleophile, the rate doubles. Or if I double the concentration of electrophile, the rate doubles. So it tells you that it's a one-to-one relationship. And if you double the concentration of both of them, the rate quadruples. So that's what lets you know. Okay, so let's do examples like I was saying. So
What did you write right after the rate equals? Is that an R?
no, it's an ugly looking cursive K. I got my first F in like 5th grade for handwriting effort. Let's go. There we go. That's a K, the rate constant. I think, did you do much of that kind of rate law stuff in general chem? Did you use like a cursive K for the rate constant? No. Not sure. Yeah, that's my cursive K. I don't even know if I can do the whole alphabet. Like, I can do a lowercase a. I'm not sure what an uppercase A is. Is it something like that maybe? I don't know. Or maybe, is that an A? I don't know. I could do B. I don't know. Is C just bigger? A, B, C, D. Oh, I think I can do a D. Is that a D? Something like that. Oh goodness, it's been so long. I don't know. All right, so let's do some examples. I'll start off like this. Here's a good one. I'll put a bromide here. So I got a halo alkane. This is usually what we're going to use as our electrophile. And this particular electrophile, this is a primary electrophile. It has the bromine is the leaving group. And so, it's leaving. So does it make sense? Someone tell me why it's called a primary electrophile. Yeah, the bromide's on a primary carbon. This is a primary carbon. It has only one other carbon attached to it. So that's a primary carbon, primary electrophile. And also it's an electrophile because the carbon has a partial positive charge to it due to the electronegativity of the bromine. Bromine's more electronegative than carbon. That's not an obvious one to predict. Let's see, let's make sure that's right. Or people agree with that. Let's look at the periodic table. Electronegativity. There's one. So see, this table is saying carbon's 2.5, bromine's 2.8. Yep, it's got it a little more electronegative. Remember, electronegativity tables can vary among sources. At 2.58 on that one. That one doesn't have it. Carbon's 2.5, chlorine's, bromine 2.8. Yeah, these are pretty consistent. And then this is a European one. They use commas instead of periods. I find that interesting. I like the periods better. Okay. So we got that. And then this will react with this primary electrophile will react with a nucleophile. I'm going to pick a really good nucleophile. Here's a good one, sodium cyanide. So you see how this carbon has a negative formal charge. So it makes sense. It's a nucleophile. Oh, and then I'll pick a good solvent for this. We'll go into the details of this, but a good solvent is one like acetone's a good one. All right, and then so again, this is our nucleophile. Nucleophile. There we go. All right, so what kind of product do we get? This is just the overall reaction I'm doing here. I'm not doing the mechanism yet. Let me move this. Okay, over here. There we go. I like it. There we go. Oh, a little further down. Overall reaction. Here we go. So our product for this one will be boom, 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 boom. Cyanide right there. Look at that. It's where the bromine was, and the sodium, just a spectator, and the bromide came off. Boom, done. And it's super easy to miscount carbons and things on this one. So let me double check. I got 1, 2, 3, 4. So this was a 1. Oh man, come on, 4. 1 bromo butane, right? It's a brominated bastard here. So this brominated bastard reacted with the cyanide, and I want to make sure it's still got the original 4 carbons of that bastard. There it is. Yep. And then the cyanide's its own carbon. So there it is. Yep. This was a substitution. We substituted bromine with a cyanide. There we go. Let's do another one. I'll do one with StereoChem. Yeah, let's get it going. Iodide. And we'll go with the sulfide. Oh, I want to make it a little bit tricky. So let's see what's going on here. We'll go potassium, this sulfide, and then we'll go DMSO, dimethyl sulfoxide. Dimethyl sulfoxide. And what we wind up with, oh, you wouldn't have guessed this maybe, but it inverts the carbon, the electrophilic carbon. And I have to make sure I don't lose all my carbons. So I'm gonna number them. 1, 2, 3, 4. Oh yeah, this sulfide's on this another bastard. 1, 2, 3. Oh, I missed one. 4. Boom. And so my sulfur started off with 3 lone pairs, right? 3 lone pairs, and now only has 2, so one of them must have become that new bond. And then the iodide came off, our leaving group. And the potassium, just a spectator, just checking it all out. A groupie. Potassium is a groupie, just watching. So, and then this is the leaving group. Change the side. Here, the leaving group, right? And actually that was the leaving group too, the bromide there. And then this here, what kind of electrophile is this? Yep, secondary electrophile. And I forget, I'd learned once how to do superscript and subscript on Google Jamboard, but I forgot. But maybe if I go, it'll look decent like that, right? Not bad. There we go. Secondary electrophile, right? And then we got the sulfide here. What is it? It is the nucleophile. Okay. Now let's look at some mechanisms. I do have a nice animation for this, and it's going to be a quiz. What's going on? Oh, it's not linked. Oh no, that's the other quiz. Why is that one not linked though? Let me reload this page. Oh, as far as the quiz coming up on Tuesday, Wednesday, these ones students miss a lot. So remember, check the key on it. Get good at the RNS. I got a lot of good tricks in this one, so make sure you don't fall for them. Did I copy this already? Copy. Oh. Link. Okay, so now it works, right? All right. This is the mechanism quiz. We're going to be doing mechanism quizzes now that we're starting to learn more reactions. And this is our, well, I guess we've already had a mechanism quiz in a way. We did the acid-base one, the big 4 acid-base reactions. So this one is more like what we're going to be doing from now on. Let's look at this initial one. Present. So the SN2 reaction, what does the S stand for in SN2? Yep. And I had a question in the chat about links, bad links in the anywhere in my course. Anytime you find a bad link or something, submit it on the extra credit for errors. Get yourself extra credit and I'll fix it for the class. Okay, so here we go. S is for substitution. What's the N? Nucleophilic. And then the 2. The 2 is the tricky one. Bimolecular rate determining step. So that means the rate determining step of this mechanism involves 2 reactants colliding and reacting. Okay, so let's look at the overall reaction. We're going to do this separate from the mechanism, as you'll see here. So in this example, I've got this molecule. What kind of molecule is this, do you predict? Do you think this is the electrophile, the nucleophile, or the solvent? Yes, this is the electrophile. And what kind of electrophile do you think it is? Is it primary, or actually it can be methyl, then primary, secondary, or tertiary? And what's with this D? What is that D there? The D is deuterium. Yep, that's a hydrogen atom, but it's a special one that has a neutron. They think they're special because they have a neutron, because most hydrogens don't. So they're like, yeah, I'm heavy. I'm double the mass. I'm more than double the mass of the most abundant isotope. They got a chip on their shoulder because there's only like 0.001% of them, but that's okay. We like them. This is a primary electrophile. Good job. And then it's a stereocenter. What is that stereocenter? Is it a R or S? Absolute configuration. What's the lowest priority for this carbon? The lowest priority is the wedged out hydrogen, the most abundant isotope hydrogen, because it's not labeled as deuterium. It's going to be we consider it the most abundant isotope hydrogen. So the priorities are A, B, C, but we're looking at it backwards. So it's S. All right. And now what's this sulfide here? What kind of molecule is that? How's it? We got our primary electrophile there. What's this sulfide doing here? The nucleophile, yep. And the potassium. What's the potassium? I think we should not call it. I think we should technically change the name. I never thought about this now, but the potassium, not a spectator ion. That's true, but I think we should call it a groupie. It's the groupie. It just kind of hangs out and watches. The nucleophiles have groupies. Okay, and now we already said this, the nucleophile, there we go. And now this down here, this is dimethyl sulfoxide. So what's its role in this one? We already got an electrophile and a nucleophile. What is it? It's the solvent. And we're going to learn shortly that we consider this solvent a polar aprotic solvent. Hopefully you can see it's polar because the sulfur is less electronegative than oxygen. So the electrons are being pulled more towards the oxygen. So the polar part makes sense. The aprotic I'll explain shortly. It means, well, one thing you could say about it is it's not protic, right? Aprotic, like achiral means not chiral, aprotic, not protic. Okay, now here's my product. Interesting, huh? Can anyone tell me something interesting about this product here? Still got 1, 2, 3, 4, 1, 2, 3, 4. Still got 4 carbons, but this iodine was replaced with the sulfide, but the deuterium was dashed and the secret hydrogen. There's a secret hydrogen. It was wedged, but now where's the secret hydrogen? Now it's dashed, huh? So this stereocenter was inverted. And let's calculate the absolute configuration of that one. So what's the absolute configuration of this one? This one should be easy, because our secret hydrogen is the lowest priority. It's back. A, B, C. It's R, huh? So this is our inverted product. We got our groupie. And what's the iodide? What do we call the iodide? The leaving group. Yep. There we go. Good. Okay, now finally for the mechanism. We've been just looking at overall reactions so far. And that's the way the science goes in real life too. You run some reactions, you get your products, and looking at the products and doing other experiments, you try to guess at a mechanism. And here's what we guess the mechanism is. I'm going to draw the primary electrophile again, but this time I'm going to show the bond between carbon, the primary carbon, and iodide is blue. And then on the sulfide nucleophile, I'm going to draw the electrons that react red, so we can follow it a little more. The product is always inverted, Alina, for an SN2 reaction. And then, so what happens is the sulfide, we believe, does a backside attack. It attacks at an angle completely opposite of the iodide, the leaving group. So it comes in like right in line with the bond between carbon and iodide, but from the back. And then the iodide pops off, it leaves, and then we get our products and our leaving group and our groupie. And this mechanism, it's only one step. Remember how halogenations of radical halogenations of organic compounds, the mechanism was initiation, propagation 1, propagation 2, terminations, all kinds of steps in the mechanism, right? For this one, just one step. So if there's only one step in the mechanism, what's the rate determining step? There's only one step. This has to be the rate determining step because it's the only step, so it's the slowest step. That's all. So how many reactants are reacting in this rate determining step? Sulfide and the electrophile, so just 2 reactants. So it has a bimolecular rate determining step. Oh, and then remember, number your carbons. I just got a text in for myself. Number your carbons. So here we go. We got carbon 1 here, 2, 3, 4, and then over here, ooh, carbon 1, 2, 3, 4. Oh, we're good. Didn't add any, didn't lose any carbons. Looking good. This mechanism, it's only one step, but you have to really have it down in your head and practice it. That's why I'm going to give you the quiz. Did I mention that was a quiz? Let me go back to that. So this is going to be a quiz. I'll make it for, I think I made it for next Monday or something. When did I say? In lab 9. Diastereomers. Then I don't have the mechanism quick. Yeah, I do. Oh, I don't know the date set for it. I'm thinking next week. I wanted to do it this week. It's best just to hit it right away. But this Thursday's throwing me off. One day off throws me off. But I'll let you know. It's going to be next like Monday or Monday, Tuesday, maybe next week, or Wednesday, Thursday. I think it should be Monday, Tuesday next week, actually. So Annalise asked about why I put so much points for the Stereochem quiz. I was thinking of it as questions I would have put on the exam 3. And so I just try to assign points, as many points as I would to that exam. So this way on that exam, I don't have to ask those 2 questions that I like to ask on every exam. That's kind of where I got the points. And I was hoping if I make the quiz worth more points, people will get motivated more to do well on it. Exam 3, I got a question from Carly. When's exam 3? Exam 3, if we go to the schedule, we'll see it. Where is the schedule? Here it is. We are at the start of week 12. Exam 3 is next week. Ooh, it is. Yep. I was thinking it was another week after that. So yeah. So Wednesday, I'll give you more details like I like to about the exam. I got to write it too. Okay. Actually, I like writing exams, kind of the things I need to do. Okay, so let's do this. I thought up a couple good examples for us to write out the overall reaction and the curved arrow mechanism for. So for the first one, I'm going to use this. I'll tell you in just a second. Okay, come on, iPad, catch up. You can do it. You can do it. All right, I'll close it. Open it again. I need to figure out a way to have my iPad wired into the internet instead of using the Wi-Fi. That would be the key, huh? But here we go. So for this first one, I'm going to go with CH3Br. Then I'm going to have it react with, what did I choose? Oh yeah, I'm going with that one. Triethylamine. And we'll go DMSO again. Dimethyl sulfoxide. Okay. So the overall products for this one are interesting in that it comes out with a plus charge on the nitrogen. And we make a salt basically, huh? So tell me what's going on with this one. What is this molecule? The CH3Br. It's a methyl what? Electrophile. We got a methyl electrophile this time, not primary, secondary, tertiary, just methyl. What's this, the role of this triethylamine? That's our nucleophile. And then in this case, our nucleophile has no charge. All the other nucleophiles we've seen so far have a negative charge. This one's neutral. So the product will result in a plus charge on the, so no negative charge. So we wind up with a plus charge over here, huh? And what's the role of this bromide? What was it? What do we call that? Leaving group. All right, so we got our overall reaction. Let's do the curved arrow mechanism. No groupies here. Nope. Groupies night off. Here's our nucleophile. I'll make its lone pair that's reacting red. And our methyl bromide, or bromomethane, I'll make the bond between the carbon and the bromine blue. So how does this work? Well, it's all in one step. It's a bimolecular rate determining step. Backside attack. Oh, gotta make this bond red, huh? There we go. Bimolecular rate determining step. Easy, right? Getting the hang of it. Nucleophile, electrophile. All right, let's do another one. Make sure we're getting the hang of it. So for this one, I'm going to go with a ring electrophile. Oh, yeah, that'll work. And then I'm going to use iodide instead of a bromide. I'll switch it up. And I'm going to go with sodium azide. That's a fun one. Sodium N3 minus. And we'll go HMPA. Hexamethyl phosphorus triamide. Some claim this is the SN2 elixir. If you need a SN2 reaction to work, you use HMPA. Hexamethyl, see how it has 6 methyls? 1, 2, 3, 4, 5, 6. Hexamethyl phosphorus triamide, three nitrogens. All right, so what do we get for this one? We get and how do you think I draw my nucleophile on here? I mean, yeah, it's after it adds. Do you think it's going to be dashed still, or will it be different? What do you think? Wedgie. We've got our sodium groupie and our iodine. We've got inversion of configuration, A, B, C. This one's R, A, B, C. This one's S. Okay. I guess we should label things again, huh? Before I do the mechanism, what is the name of this reactant? What do we call that? It's an electrophile, yes. And what kind of electrophile is it? Secondary electrophile. And what do we call the iodide here? Secondary electrophile, I'm sorry, secondary electrophile because it has 2 carbons attached to that carbon with the iodide. All right, and then what do we call that leaving group? It's called the leaving group. I just said what it was and it left. That's the leaving group. Okay. All right, and then what's this N3 minus thing? What's it called? What's it called? the nucleophile. Good. And then this here is our solvent. We'll talk later. It's a polar about this polar aprotic solvent. We'll define that shortly. And we did invert the stereocenter. Inversion of configuration. You always get inversion of configuration with SN2. Okay, let's do the mechanism. I'll draw my leaving group with a blue dashed bond. And then my nucleophile, I'm going to draw it out. This one's an interesting has a very interesting Lewis structure to it. You can draw it this way. Has resonance. Oh, wait. That's what I want to do. That's what I want to do. It's a major resonance structure. Let's go 1, 2, 3, 4, 5, 6. Yeah, 5 minus 1, 2, 3, 4, 5, 6. You see the pluses and minuses. All that adds up to -1, right? Azide, it's a strong nucleophile, a poison as well. Poisonous. Most strong nucleophiles we consider poisonous probably. But I used it in biochem. I remember we would put dilute solutions of sodium azide in equipment we wanted to store that we didn't want any mold or bacteria or viruses to grow in. So you'd keep them in the poisonous sodium azide solution and then rinse it out before you used it. Okay, so how does this work? This azide nucleophile comes in, does a backside attack, bam, hits that carbon. Leaving group leaves all at the same time. So it's a bimolecular, I'll take it. Bimolecular rate determining step. There we go. And our product is the following. A wedged out group there, and then that nitrogen of the azide looks like so. And now you can see why that is. N3, it's neutral overall because you have a +1 and a -1. Okay, and we also have our leaving group that left. And it has a blue pair of electrons as well because it came from that bond there. Okay. Hopefully we're getting the feel for this. Be a little more specific down here. There we go. Now I want to show you how we think this whole inversion of configuration works. Let me first show you an example with some stereochem. So I'll do an overall on the mechanism. Going down. So I have the bromide. What kind of electrophile is this? Secondary electrophile, good job. And I'll go with HMPA again. Oh, no, I'm switching it up, huh? I'm gonna go DMF. DMF. So that's dimethyl formamide. Oops. I'm just kind of introducing a lot of these solvents that are used, common solvents for SN2s, and we'll talk more about them later. You don't have to like memorize them all. We'll just kind of use them and you'll get the hang of it. All right, so we got DMF in there. And so our product, hopefully you're starting to see this already and you're like, yeah, it'll be dashed like that, right? And you have the bromide and the sodium groupie. Just watching. Okay, for the mechanism on this one, I'm going to draw it out slow and add the transition state to it. Oh, and then, so if I want to add the transition state, let's do it proper. Let's say this is an exothermic reaction. XO, boom. Okay, good enough. So I'm going to take my cyanide. I'm going to draw it on the right here with a red pair of reacting electrons. And then my bromide, I'm going to twist it around and draw it differently. Oh, but I want to draw it with a blue bond. If you haven't noticed, I think of negative charge things as red and then positive as blue. There we go. So I'm going to draw it in a way where I can see the backside attack happening. And I want to make sure I draw the same molecule though. So I need to know whether to put, I'm going to put the H here so it's easy to assign R and S to. And now I have to decide whether I want to put the ethyl here or the methyl or the ethyl or the methyl. Let's look at the stereochem of the starting molecule. So the starting molecule is ABC, what is this, R or S? R. And then the product is ABC, but I got to go backwards. This is S. So this needs to be R. So I'm just going to guess and check. If I put the ethyl up top, will it be R still? It needs to be R like this. Let's go. A, B, C. Oh, wait, it's S. I don't want to do that. Let me undo that. Let me put this here. That's where the ethyl needs to go. Now it's still R. Because the lowest priority is back. B, bromine's first priority, second, third, A, B, C. Looking like R. Okay, so I have the same molecule. Let me move it over a little bit too. So it's going to be backside attack. That's what we talk about, huh? Backside attack right there. And people make memes about the whole backside attack thing, but yeah, just remember SN2 backside attack. So, and as the cyanide's adding to that carbon, the bromine bond is breaking away. And if it's exothermic, let me just do a little mini reaction coordinate diagram here. I'll do a bigger one later. It's going to look, oh, I don't know, that's endothermic. It's going to look more like what, reactants or products? Going to look more like reactants, yes. But it's going to start making a product approach. And so, but this bond's going to be a bit longer, right? The carbon, cyanide carbon to the other carbon is going to be a bit longer. And, but then this, do you see how this, these guys are going to start to flex to the left? This is the whole key to the inversion. Let me make sure I do a good job of it. So it's still a little bit this way, but this methyl, it starts to go this way. See how it's going that way? And the ethyl as well, and the hydrogen, they're starting to go this way. They're getting inverted that way. what I'm doing here, I'm drawing the transition state before I go to the product. And the product, of course, will look like this. I'm kind of running out of room, but I think I could squeeze it in. And this stereo center is now A, B, C, it's S, just like above. No, but I haven't added my formal charges, my partial charges. So the cyanide starts off a full -1. It's still closer to -1 than 0 in the product. So I'm gonna go -3/4. The bromide starts off as nothing, but it's gaining some negative charge, but it's only just starting to gain the negative charge. So I'm going -1/4. All right, and then in the product side, I also have the bromide that came all the way off. There we go. And now that transition state, can you see how that stereo center is getting inverted? And that's what we believe happens. The backside attack inverts the configuration of the stereos of the electrophilic carbon. And that's why we get changes in stereochem. Oh wait, I said more. I keep on saying, did I say it looks more like products many times? It looks more like reactants. I hope I've been saying that. Okay, good. All right, so there's our transition state, and hopefully you can start to see how the backside attack works. Let's look at them. Let's look at some examples online. Some of these are okay. Let's do SN2 backside attack animation. Let's see if this one's any good.
People with ADHD say
That's not that good. I wanted the full-on like animated one. This one might be good. Is it good? Oh, it's kind of good. This middle one, what do you think? This is the green is the nucleophile coming in. Boom, and it kicks out the leaving group. You see how those little white ones, they get inverted? Whoop. Not bad. I've seen better. I think those sometimes these, because they're big puffy balls, they're not as good, I don't know, as they're not as good as the Corbeil mechanisms for you to learn it, I think. It's interesting. Anyway, so we got that. Now, let me do another one. So the inversion of configuration, we believe it happens all the time with SN2. It doesn't need to have a stereo center for it to occur. So if I had just like this guy, the chlorine on here, and I added, I'm trying to think of another good one. I'll do the hydrogen sulfide. That's one of the best. We'll go acetone. So right now, can you tell there was an inversion of configuration? You can't really tell, right? Because it's just the same. There's no stereochem. And again, yeah, this is a primary electrophile, the leaving group, and that's the nucleophile, of course. This would be exothermic as well. So let me draw the mechanism over here like I did on the other one. I don't really need to draw it in all the details that I'm about to, because it has no stereochemistry. But I want to just point out the fact that we think it always inverts. So like if I have an H here, an H there, and my chloride here, the hydrogen sulfide does a backside attack, breaks the leaving group off, which I left as hydrogens out, didn't I? So in the transition state, it's gonna look like more like reactants since it's exothermic. But these hydrogens are gonna be flexing to the right. Same with the methyl. It's gonna be a little more to the left, but it definitely came that way, right? So this is going that way, that's going that way, that's going that way. And then the chloride is leaving, but it's still a little closer because it's reactant-like. All right, there's our transition state. That was kind of ugly, huh? Trying to do this one fast because I want to get to a good stopping point. And so these H's now are all the way over here. But since there's no stereochemistry, it doesn't really matter that I show the inversion, but I want you to understand there is inversion, just to always get inversion. And the charges. So what's this, the partial charge on the sulfur? It looks more like reactants. Yep, it's going to look more negative because it's closer to reactants. And the chloride, the chlorine in the transition state looks more like reactants. So what does it look like? Minus a fourth. Yeah, easy, right? Oops. There we go. Got it. And then I just want to draw the reaction corner diagram fully on the next page. Well, actually, I can squeeze it in here. It's pretty simple. The transition state's maybe the hardest thing to draw, which we just did. So here we go. We got energy, reaction, coordinate, right? Oh. It's exothermic. We've got our sodium sulfide, sodium hydrogen sulfide, and our electrophile, our primary electrophile, and our products. Sodium chloride. Activation energy for the rate determining step, the only step. And there's the transition state, which we have drawn there. Piece of cake. And I haven't gone over a lot of this yet. Got some good examples here. You could try drawing out the curved arrow mechanism for all these. It's a good practice.